Alright, so we're going to start with number 2 here. We just discussed how WebAssign was being wacky on the entering of it. Do you want me to start with part 2 or part 3? 2. I'm assuming most people got part 1, right? Yes? Okay, so let's start with part 2 here. And so we're going to do, this is going to be number 2. And this one would actually, if you were doing this like on a test or an in-class problem set, you'd have 3 force diagrams, 3 free bodies. I'm going to do the force diagrams for part 2 and part 3. So let's see. I have this. I have my force P. I would have force of gravity or the weight down, and I'd have the normal force up. And then, I've got to put it up that way. Here, I've got P, force normal, and gravitational force. So those would be my force diagrams for this. That would be the part that counted for whatever points it applied. And then I would go down to start in on my how, with the free body here. And I did, oh, by the way, I put more of these sheets in the back. I actually made them double-sided with the same format we used yesterday. If you want them, they're back there. I'm going to do number 2. So for number 2, got this. I've got F sub G, F sub N, and then I have P, and I think P was at angle theta. Yeah, angle theta there. So over on the side here, I'm going to deconstruct P into its vertical part, which is downwards, its horizontal part, which is horizontal theta here. So this side is P cosine theta, and this side is P sine theta. Right? Doing the component part of it. I know my head's probably in the way. I would do the same thing over here for part 3. Right? FG, force normal, P in this direction. Now the difference is that when I deconstruct my P, I get my vertical component as opposed to my horizontal. I want one of the new smartboards. You can just click the button and it changes the color. P cosine theta is the same here. But now over here where I'm running out of space, it's P sine theta also. But this time it's upwards, where in part 2 it's downwards. So that changes, whether it's a positive or a negative force. So continuing on with number 2 here. In the x direction, I have we'll do number 2 up top here and number 3 down the bottom. So this will be number 3 down here, and this will be number 2 up here. And horizontally, I have P cosine theta and P cosine theta. Vertically, F sub G, force normal. In this case, I also have the down of P sine theta. In this case, F sub G, force normal, and up of P sine theta. So that's really the big difference there. And then, you guys okay if I do number 2 over here, and number 3 here? Yeah. In the case, I'm not worried about the horizontal because they didn't ask me in the question about the horizontal. But would I have an acceleration horizontally in this? Yeah, I actually would because I have a net force. That's where the problem is a little bit screwed up in they say it doesn't accelerate, but there's no friction, which would be impossible. But we're not worried about the horizontal. We're only worried about the vertical. And so I have my one equation, sum of the forces is MA, and in this case I'm in the Y direction. And I've got force normal in the positive, right? Everything else is in the negative. See how I've got the negative P sine theta and negative FG. Negative P sine theta, negative F sub G equals no acceleration, so M times 0. So I end up with force normal after I rearrange equals F sub G plus P sine theta. And I know that F sub G from my equation sheet is mg plus P sine theta. Yeah? Okay. And then for number 3, very, very similar. Except my P sine theta has flipped, so I have Fn plus P sine theta because now it points upwards, right? They're upwards together, minus F sub G equals 0. And so rearranging, I get Fn equals Fg minus P sine theta. And so my force normal is mg minus P sine theta. And we have that weird way we have to put it in. Alright, so let me demonstrate that weird way again. That weird way is I type in my mg, and then I'm going to do minus, put in the sine, put in the theta, make sure that the theta is lowercase, and then I'm going to put in my uppercase P, shift P, change it to look at the uppercase psi, and parentheses, theta, parentheses, and what that is going to be understood as correct in this screwed up answer. But it's mg minus P sine theta. So your correct answer with the screw up should look like that. All right? All right, so we're going to do number 3. You make a slingshot with a rather long, wide rubber band, practice hurling pebbles. The force of this and the angle between the two halves is this. What is the tension in the band? Okay. So, let's start off drawing our elastic band. And then I'm pulling this way with a force. Now, it's a continuous band, okay? So, and I can even add, I'm looking kind of down on mine, so there's the branches of my slingshot. It's a continuous band, so the tension in it is going to be the same throughout. All right, so it's going to pull back with a force of tension here, and that's going to be equal to the force of tension here. Those two are going to be the same. And it tells me is 123 degrees. So that says that this angle that I've drawn really small is 123 degrees. Yes? So, taking this down to my free body now, start with my dot. I'm going to have F. I'm going to have F sub t, F sub t, and the angle between them is 123 degrees. So what I'm going to do is I'm going to do the components of F sub t. And if I take and I draw in these horizontal components, you okay over there? Okay. And the vertical components, I know this, if they split this angle, because you're in the middle of it. So that means each one, in my case, gets 61 and a half. All right. And now I can label those components. Both of these would be the same. They'd be ft cosine of 61.5 degrees. And then my reds, nicely balanced there, ft sine 61.5 degrees. And ft sine 61.5. You know, if you weren't sure of the that this was the same tension because it was a single rubber band, that you could label these ft1 and ft2, and you'd end up finding as you went along that they were equal to each other. All right, so you'd end up with the same thing. They want to know what that tension is, and so here's where I'm going to be selective, and well, I'm going to do both, but you may not have to do both sides. I'm going to do the free body for both sides. So in my X free body and my Y free body. Now, as you get better at these and you see, oh, wait a minute, I don't really need to do that free body, you know, because I'm only interested in that side. Feel free to not do anything on the other side. You know? But especially when you're starting off, if you don't see the relationships, then make sure you do both. And we have ft cosine 61.5 and ft cosine 61.5 ft sine. Alright, so I'm interested in F. I'm not even going to bother with the vertical side, but if I hadn't recognized that the two tensions were the same, that's where I do the vertical side and prove that, hey, they're both tension on each side is the same. So I only have to find it once. That's the advantage of that vertical side there. So here on the horizontal, I'm going to set up my equation with my one equation. And I have three forces. You guys want to call to the right positive? Yeah? Okay. So we'd have I'm going to move this up a little bit, negative F plus ft cosine 61.5 degrees plus ft cosine 61.5 degrees equals m, and we're not moving, so we're not accelerating, so we have 0 over there. Yes? So, rearranging this, I get F equals 2 times ft cosine 61.5 degrees. And they want me to find the tension, so I'm going to rearrange that so I have the tension by itself. I'm going to get F over 2 cosine 61.5 degrees equals the tension. And now it's just plugging in my numbers. They tell me F is 2.52 newtons. So 2.52 newtons divided by 2 cosine 61.5 degrees equals my force of tension. And so my force of tension is let's see. I get 2.64. See if that's right. Yeah. Yay! Alright, so we're going on to number 4. Traffic lights assigned for 2 cables is shown. Oh, we had like almost this exact problem yesterday, didn't we? We go to part C, maybe, of the packet that we worked through yesterday. And we had this almost this exact one. But let's do it. I'm gonna grab this so I don't have to redraw it. They did such a nice job drawing it. See how that came through. So this is number 4. So in this case, I'm going to actually center in on this junction here and put that there's the weight down, FT and FT. Do I think those are the same values? No. So I'm going to label this FT1 and this one FT2. And I can almost directly transfer that down here to my free body. In FG, FT2, FT1. And let's see, they told me a couple angles here, didn't they? 60 degrees up there, and then 30 degrees up there. So if I draw this one, and it's 60 up here, that means this is also 60, opposite interior angles, something like that, one of those geometric things. And then I'll draw this one over here, same type of logic. If up at the top it's 30, down here it's 30, and FT2, so then giving my horizontals and my verticals. This side would be FT2 sine 30, and this one is FT1 sine 60. And so this would be FT1 cosine 60, and this is FT2 cosine 30. Any problems up to this point? All right, so now I'm going to just do my horizontal and my verticals. In my horizontals, I'm going to have 2 forces. In my verticals, I'm going to have 3, the reds and then the gravity. All right, so I'll see if I can do this from memory. We would have F T2 cosine 30 degrees and F T1 cosine 60 degrees. In the y direction, we're going to have the weight down still, upwards, 2 forces, and of course those would be red. Ft2 sine 30 and Ft1 sine 60. And we want to know what T1 and T2 are. Looking at it, what my thoughts go to is that I only have T1 and T2 in my horizontal free body. So that's going to that's relating the 2 of them to each other, right? And over here, I've got T1 and T2, but I also have the weight of the object, so that's relating them to the weight. So I'm going to have, in my mind right now, I'm thinking I'm going to have to use both sides. I'm going to find how they're related to each other on the x side, and then how they're related to the weight on the y side, because I know the weight of this, right? I know its mass, 12.8 kilograms, and so I can use that the weight is the mass times the gravitational field. Knowing that mass, I can find its weight. So the weight is kind of the thing I know. So let me start on this side, on the vertical. Sum of the forces in the y equals MAY. Hopefully you've noticed every time that's where we start, right? And we have Ft1 sine of 60 plus Ft2 sine of 30 minus F sub g equals m times 0. And then can't do a whole lot. Sine of 30 equals F sub g. And so all of that equals m times g, which equals, what did I say mine was, 12 something, 12.8 kilograms times 9.80 newtons per kilogram. But I really can't combine those yet, right? Because I don't know T1 or T2. So this is where I switch over to the other side and say sum of the forces in the x, MAX. And I do F T1 cosine 60, have to be negative, plus Ft2 cosine 30 degrees equals m times 0. Now, if it makes, go one more step, so I end up with Ft2 cosine 30 equals Ft1 cosine 60. And I'm stuck kind of at the same point. I have Ft1 and Ft2. I have them over here also. but I can't go any further. So what I'm going to do is it's either at this point I could put this into something to solve the equations for me, or I can do the algebra. All right? Should we do the algebra? Or no? Yes. Okay. Which one do you want to solve for first? T1 or T2? T1. Okay. So to solve for T1 means I need to get T2 out of the red side. That's going to let me solve for a value. This is telling me how they're related to each other. So I'm going to do this FT2 equals FT1 times cosine 60 degrees over cosine 30 degrees. I'll let that sink in for a second how I got that. Sunk in? Okay. I'm going to actually figure out the number of that now. Calculator. Cosine of 60 divided by cosine of 30. Yay, that's a happy number. So it's that number, 0.57735.02692. That times T1 equals T2. So which one's bigger, T1 or T2? T1 is bigger, right? T2 is about half the size of it. So now I'm going to use that over here and substitute in that for T2. So I'm going to have FT1 sine 60 plus FT1 0.577, you'd be lazy, sine 30 equals, let's do that 12.8 times 9.8 and see what we get. 12.8 times 9.8, 125.44. 125.44. Oh good, I'm down to one variable. So I'm going to pull that out in my next algebraic step. Good, I'm almost out of paper too. FT1 times sine of 60 plus 0.577 times sine of 30 equals the 125.44. So then solve for FT1. So let's see, 125.44 divided by parentheses, and I need to divide it by this whole thing that's multiplied by FT1. So that's sine of 60, sine 60 plus my 0.577. I don't feel like typing again. Which is times sine of 30, is it? Yeah. Times sine of 30. Close that parentheses. Close that parentheses. Hope that I closed all the ones correctly. And I get 108.634. Call that 109. going to substitute that in over here to get FT2 equals 108.6 newtons times my 0.577 to get FT2. Back to my calculator. That number times that number, and I get 62.7. Let's hope that's right. 2.7. So let's see if I work my calculator. 109 and 60. So let's go. This is where I gotta make sure I put them in the right side. I said FT1 was the right-hand cable. Yeah. Oh, left-hand. FT1 is the left-hand cable. So that should be 109. And then 62.7. See if I got it. Excellent. So, any questions